Okay, can you see the screen?
Yes.
Yes.
Okay, thank you. So thank you very much for the invitation. So Abhijit wrote to me about, I think in January, to give a talk. And by that time, I had already committed to giving a talk at ICTS in February. So I told him, okay, please fix it on April. Maybe I'll have something new to say. Unfortunately, I don't have any concrete results. Okay, but what I'm planning to do is to just tell you about some work in progress. Okay. So here is a disclaimer. Okay, the first I have already said, this is based on some work in progress. We shouldn't trust any factors of 2 in various formulae, not because they are not important, but just because I have not fixed them yet. I have not been able to fix all the factors of 2, and it changes every few days. These are probably okay, because these have stabilized for last 2 months at least. Okay, so factors of GS and pi are most likely okay, and I'll explain some of these. And finally, our notations for coupling constants and amplitudes more or less will follow the ones that are given in Polchinski's book. Okay, although again here I may miss some factors of 2. So let me begin by describing the problem that we want to address. And here is the problem. So let's suppose that we consider 4 graviton scattering amplitude in type 2B string theory. Now it's known that at tree level, it's given by the supergravity result. And then there's an additional R⁴ contact interaction. And this is obtained simply by taking the string amplitude for 4 gravitons and expanding in powers of the Mandelstam variables, ST and U. So this is the structure of the amplitude. So this is the usual momentum conserving delta function. Kappa here is the gravitational coupling constant. Kappa square is 8 pi g. And this is related to the string coupling, G string, okay, by this formula over here, where G string in our notation is defined in such a way that the D string tension is 1 over 2 pi gs. Okay, that's my definition of what string coupling is. So this relation basically follows from Polchinski's calculation of the D-Brent tension. Okay, so he expressed the tension in terms of kappa. But here, by normalizing the G string in this way, I have expressed kappa in terms of G string. So this is a kinematic factor. Okay, this depends on the coordinate and not coordinate. This is polarizations and momenta of external gravitons. And in particular, it carries 8 powers of momentum. And in this formula, all the momenta are measured in string metric. So I have not written down the explicit form for this Kc. Okay, but this is again following the same notation as Polchinski's book. Okay, sometimes it's written as T8, T8 R⁴, but this is a standard structure that one always uses. Okay. So this is the contact term. Okay, so this is the supergravity contribution, and this is the contact term that one gets by expanding the 4-point amplitude. So what one can show is that the first term, okay, this is a supergravity contribution. This is S duality invariant. It doesn't look so in this form because this kappa, of course, depends on G string. But once you express everything in terms of the canonical metric, okay, not the string metric, but when all the momenta are measured in terms of the canonical Einstein metric, the G string goes away. And one can show that this is S duality invariant. But this one by itself is not S duality invariant. But we know that there is an S duality invariant completion of this term. And that includes one loop contribution and non-perturbative terms. And it's written as the non-holomorphic Eisenstein series. But what I have given here is an expansion of that in for small weak coupling. So this is the original term, the Gauss-Witten term. This is the one loop contribution. This, in fact, was calculated before the tree-level contribution by Green and Schwartz and Brink. And then there are a whole lot of non-perturbative corrections which are given here. Okay, so my notation here is tau is A plus I over GS. A is the vacuum expectation value of the Ramond scalar. And in this expansion, this is the D-instanton contribution, and this is the anti-D-instanton contribution. Tau star is the complex conjugate of tau. And of course, these are even for instanton, there are power law corrections. Okay, there are corrections in powers of G string, and then there are 2 instanton and 3 instanton corrections. Okay, none of which I have written down here. So this calculation gives a definite prediction for the leading D-instanton contribution to the 4 graviton amplitude. Okay, so I just take this and pick up the coefficient of this term over here, and then use this fact that tau is A plus I over GS. And this is the prediction. Okay. Comes with very precise coefficients. You have this factor of e to the 2 pi IA because of the tau contains this factor of A. And the question you want to address is it possible to reproduce this? This is a prediction of S duality. But is it possible to reproduce this directly from D-instanton computation?
Ashok, question.
Yes.
At some point, Sethi and Green had tried to reproduce the same result as a consequence largely of supersymmetry, if I remember right.
That's right, yes.
And so supersymmetry plus, so assuming just supersymmetry, can we also, could we also say this is a prediction not of duality but of supersymmetry?
No, I think you need duality, because you use, see, Green and Gupta, the original prediction was not even approved. I mean, because they couldn't prove that non-holomorphic isosceles series is the only thing which is S-duality invariant and satisfies the appropriate requirements. What Green and Sethi proved is that if we assume S-duality invariance, and then they proved that this function of tau and tau bar satisfies the differential equation. So S-duality invariance together with the differential equation fix the form of the function.
I see, and that the harmonic differential equation was not enough by itself to fix.
No, that was not enough by itself to fix.
I see, thank you.
Yeah.
Okay.
Yeah.
Okay.
Okay. Any other question at this stage?
Ashok, I forgot whether you got to the last line of this transparency or not, but I have a question. I don't know if
yes, okay, I have not got, but okay. So basically, I was giving a motivation for this, that if one understands how to do this D-instanton calculation, then in principle, we can apply it to cases where the result is not known. And in particular, that involves, for example, the D-instanton in the superpotential in n equal to 1 supersymmetric string compactifications.
So Ashok, sorry, this is a tangent for your talk, but in some cases, at least, if I recall right, holomorphicity and kind of Seiberg-like arguments could fix the D-instanton contribution of the full n equals 1 superpotential. Is that not true?
You have a, in quantum field theory, you are suggesting?
No, I thought even in string theory, because the axion shift symmetry and so on, the Raymond, this A.
Yeah, but I think the overall normalization will be hard to fix.
Overall.
That argument.
Yeah, okay.
Because here you are really talking about the normalization.
Okay.
That's what you want to get.
I see. Yeah. That's certainly true. Okay, thank you.
I have a very remedial question. So in the previous slide, you showed this the S duality completion of this zeta function term.
Yes.
That completion is unique. I mean, S duality uniquely fixes this.
Yeah. So I think originally when Green and Gutperle proposed it, they couldn't prove that it's unique because it's non-holomorphic, right? So the constraints are much less. But then Green and Sethi proved that this by supersymmetry imposes some differential equation on this function.
I see.
And I think with the differential equation and S duality invariance, this completion is unique.
Okay.
So just S duality invariance doesn't uniquely.
It's a space-time supersymmetry. N equal to 1 space-time supersymmetry.
Exactly. So you need the space-time supersymmetry and S duality to fix this.
Okay, thanks. Yeah.
Okay. So if you look at this structure, the dependence on the vacuum expression value of the Ramon scalar, that can be inferred from general arguments. But it's also true at the same time that A doesn't directly appear in perturbation theory. So what we can really calculate reliably is how things change when you shift A. Okay, when you change A, okay, the change under the of the amplitude under the change in N can be calculated. So because of this, the overall phase of the amplitude can be absorbed into a redefinition of A. Okay, we can simply shift A and absorb an overall phase. So for this reason, we will not try to determine the overall phase of the amplitude because that can be observed in A. And indeed, the overall phase we'll see is somewhat ambiguous because you have to evaluate a chiral formula determinant. So it's just as well that this A is there. This e to the minus 2 pi by gs is simply a reflection of the fact that the D-instanton action is 2 pi by gs. Okay, so that's always there. And so the goal is to reproduce the rest, this factor. And in fact, here I should add that the GS dependence was understood some time ago by the Harvard group. Okay, and they used essentially very similar to the line of argument that I'll describe. Okay, this is still not published. Okay, because I think they looked at it in the context of C equal to 1 matrix model, but they also determined at the same time the 2B GS dependence. So, but what we want to fix is really this part. Okay, so factors of 2 and pi are not unimportant. Okay, this is what we are after. Okay, but we'll also see how the GS dependence comes as we.
So, and the KC dependence, the polarization dependence comes immediately from supersymmetry?
Well, yeah, it comes immediately from supersymmetry, but it can also be seen. I mean, when you do the calculation, of course, you don't use supersymmetry directly, but KC comes out automatically when you calculate the amplitude.
Okay, thank you.
And we'll see how KC comes eventually. Okay, so here, as I said, this is our goal. Okay, and the current status of the calculation, as I have already said, that we can explain the result up to powers of 2. Okay, and powers of 2 has not yet settled to the fixed point of the calculation. Okay, so hopefully that will happen. So you cannot even say whether it agrees or not, doesn't agree. But I'll try to show how the factors of pi at least come about. Okay, and in that process, we'll also learn this GS dependence. And this analysis will follow more or less the same procedure that was used for computing the normalization of the D-instanton amplitudes in two-dimensional string theory. Okay, this is something I describe in the ICTS talk, but this will be independent. Okay, but it's basically the same kind of procedure. Okay, so now let me begin with the analysis. So naively, the leading contribution, okay, we are now looking at from the worldsheet viewpoint. The leading contribution comes from the product of 4 disk one-point functions, an arbitrary number of annulus one-point functions. So this is what I've written. So I'll explain what this various, why this is the leading contribution. So this is a product of just simple one-point function on the disk. Okay, that's and what enters at the center, the vortex operator, is the graviton vortex operator, because I'm trying to calculate the 4 graviton vortex. So let's try to do the counting the powers of G string. Okay. So first of all, because it's a single D-instanton amplitude, you always have this e to the minus 2 pi by gs. Okay. And then the rest of the powers of G string comes as follows. So here, because disk has Euler number 1, okay, it comes with a GS inverse. Okay. And the closed string vortex operator carries the factor of GS. Okay, so each of these gives you GS to the 0. Okay, so that's why this is GS to the 0. Okay. And the annulus, okay, because it's Euler number 0 and it has no vortex operator, okay, it's always GS to the 0. So you can, given this, you can insert arbitrary number of annulus diagrams. And that's what I have summarized by saying that this is exponential of the annulus, okay, which means you can have no annulus, you can have 1 annulus, you can have 2 annulus, and so on. Okay, and the combinatoric factor works out correctly. This I is the standard factor that appears in the expression for the S matrix, right? When you can relate the string worldsheet amplitudes to S matrix, there is always a factor of I that comes in from. So naively, then it's given by e to the minus 2 pi by gs times something order gs to the 0, okay, which obviously is in contradiction with what you see here. Right? We had this gs to the 7.5. But this, of course, is not quite the right answer, and for reasons that I'll explain. So the main subtle point is in calculating this. Okay, in fact, at this order, these are more or less straightforward. These are no divergences. Okay, we can calculate this. But this is the subtle calculation. And most of this talk will be focused on this. Okay, and then we'll put everything together. So you define n to be
yeah. So you are doing a Euclidean calculation, right? I mean, because it's a D-instanton. And so this e to the power minus 2 pi over gs where do you get this number from? I mean, it's like the D-instanton action is 1. Is that the point?
No, D-instanton action is 2 pi by gs.
2 pi by gs. So 1 over gs is just sitting outside, I presume, just like it happens for the, I mean, if
All
I...
D-branes have 1 over D-brane tension, right?
Right, and the 2 pi, I see. So the 2 pi is the value of the classical action for D-instanton.
So basically what happens if you normalize so that the D string is 1 over 2 pi gs, then every time you add a dimension, you have a 1 over 2 pi, right? So D2 brane will be 1 over 4 pi, or D3 brane will be 1 over 2 pi to the cube gs, right? And if you go the other way, right, the D-instanton will be multiplied by a factor of 2 pi square. And that's what gives us 2 pi by gs.
And there is no action, of course. I mean, in the sense that there is no action integral kind of thing, because it's just D-instanton. That's what you mean. I mean, you know, like for D0 brane and D1 brane and so on and so forth, there will be an integral to evaluate.
Those are all here. See that those integrals are all here, right? The worldsheet expression, you're talking about the fluctuations of the modes, right? On the D brane.
No, I was talking about the classical evaluation
the
of
the coordinate of the brane.
Yeah.
That's also hidden here. We'll see.
Okay, I see.
So everything is hidden here because string worldsheet by itself doesn't tell us to do anything more, right? If you just look at the string worldsheet, it tells you you calculate this, right?
Right.
So all those integrals will be hidden here inside this.
Okay.
So you have to basically extract those where the collective mode integrations are in this from these diagrams.
Ashok, can I ask a very stupid question? Please forgive me.
Okay.
Why are we only having the 4 gravitons in disconnected disks? Is it because we are after a contact term? I mean, couldn't we have...
Those will be higher order. You are thinking of 2 gravitons on one disk, right?
Yeah. I see.
Yeah, but because disk gives you 1 over G string, because Euler number minus 1, Euler number 1.
Yes.
And each of the gravitons carry G string.
Okay.
So that will be ordered GS.
I see. Okay.
So leading contribution is just this. Okay, you have to basically maximize the number of disks you can get. Right? 4 gravitons, you can get 4 disks.
Okay. Thank
you.
you.
If you have a supersymmetric partner of this will be 16 fermion, right? And there is basically the product of 16 disks.
I see.
Okay, that's how you maximize the power. That's the leading contribution.
I see. Thank you.
Okay, so now one point here. Okay, the naively one might have expected that this should be proportional to the individual momentum conserving delta function because it's disconnected diagram. Okay, and indeed in normal string amplitudes you don't include disconnected diagrams precisely because of this. But because you have D-instanton boundary condition, I should have said all these boundaries have D-instanton boundary condition. Okay, single D-instanton, so all of them land on the same D-instanton. So because of this D-instanton boundary condition, the individual disk amplitudes do not conserve energy and momentum. Okay, because translation invariance is broken. The D-instanton is located at some particular point. So the momentum conservation, in fact, will be restored at the end after you integrate over the collective coordinates, okay, which you don't see yet from this, and we'll see how they emerge from these diagrams. Okay. And these I'll discuss later. Okay, but this is something we kept in mind that we are including this, okay, even because you don't have separate momentum conserving delta function. But at this stage, we have no momentum conserving delta function at all.
Yeah.
Okay, if we just naively look like this.
Yeah, that is what was confusing me because normally if you had these disconnected ones, you would separately conserve the.
Yeah, exactly. Yeah, but that's not the case here. In fact, here you don't conserve anything as it stands.
Okay. Thank you.
It's only after you integrate over the location of the D-instanton that you can recover momentum conservation.
Yeah.
But that we haven't seen yet, right, from this diagram. Okay, so this A is the annulus amplitude. I think I've already introduced. Yeah, so I call this A. And this can be calculated. Okay, it can be calculated from open string spectrum or from boundary state. Okay, for type 2B D-instanton, so you know what A is. So this is the explicit expression for the annulus partition function. So these are the Jacobi theta functions. Okay, and last time, in fact, is identical as 0, but I have written it just to make it look symmetric. Okay. And indeed, A actually vanishes by theta function identity. Because it's essentially a result of cancellation between the Neveu-Schwarz and Ramon sector open string states, okay, because the spectrum is supersymmetric. Okay. So A basically is calculating the trace of e to the minus 2 pi t L naught, okay, weighted by other minus 1 to the f, okay, where f is the worldsheet fermion number. So it basically space-time fermion number. And this cancels between Neveu-Schwarz and Ramon states. So these two are contribution to Neveu-Schwarz sector, and these two are contributions to the Ramon sector. So if we take this literally, then we'll conclude that n is I. Okay, and we are back to the problem that we had started with, namely that is it's G string to the 0, no G string dependence at all, no momentum is conserved. Okay, but that's of course not true, because you have to treat the 0 modes carefully. Okay, and that's what we will have to do now. So this is what we expect of a general structure of A, okay, that it should be like trace of e to the minus 2 pi t L naught. T is basically the, if you take the annulus width to be pi, then T is the circumference of the annulus. And this is weighted by minus 1 to the f. So you count 1 for bosons, that means 1 for the NS sector, minus 1 for the Ramon sector. Now the fact that the A vanishes, that the integrand vanishes, as I said, it's not trustable for the L0 equal to 0 sector, that we have to deal with separately. But at least it shows that for positive L0s, this cancellation is genuine. Okay, they really cancel, there is a Bose-Fermi pair cancellation. And that means that all the subtleties are, in the whole computation, you can just restrict our analysis to the L0 equal to 0 sector, right? You can just forget about the L0 positive sector altogether, because there is no subtlety there. So the 0 modes you have to treat carefully. Okay. And although this is not strictly necessary, I mean, it will be useful to, as we go along, to regulate the 0 modes, okay, by adding a small non-zero L0 value. Okay. And one way to do this, okay, if you want to have a concrete system that has the same spectrum except that L0 has some added value, either we could consider, instead of, here you're talking, this is the partition function on a single D-instanton, okay, the open strings which start and end on the same D-instanton. Okay. We could, for example, consider the partition function of open strings that start on one D-instanton and end on a neighboring D-instanton, okay, which is close by. Okay. And the point is that the spectrum of that open string is identical to the spectrum of the open string which both ends lying on the same D-instanton, okay, when the two D-instantons coincide. So you can just regulate this by saying that we take open strings going from one D-instanton to another D-instanton, okay, calculate its partition function, and then we'll try to take the 0 separation limit and see what's going on. Okay, so this is just a convenient regularization of the L0s. Okay, so we'll just keep this in mind.
Ashok, wouldn't there be a factor of 4 when you take the coin? I mean, in the sense that there will be 4
indeed.
types of,
yeah. So I'm just taking one of those sectors. The sector that considers a construct takes an open string going from one to another. Okay. Or if you think in terms of Chan-Paton factor, right, there is identity and sigma 3, which are the diagonal ones.
Okay.
And then sigma 1 and sigma 2, you can say, okay, let's focus on Chan-Paton factor sigma 1.
Okay.
So that has the same spectrum as that identity.
Ashok, how many 0 modes are there?
Here we'll do the counting.
Okay.
We'll see that there are, okay, let me just proceed a little bit and then it will become clearer probably, right? It depends on whether you count only the physical 0 modes or the ghost 0 modes and so on. Okay. So if you just want the number, I can tell you right now, there will be 10 bosonic 0 modes, okay, 2 fermionic 0 modes from the ghosts, and 16 fermion 0 modes from the Ramon sector. That will be the counting, but we'll see this explicitly as we proceed.
Will this account for that 7/2?
It will indeed, but you have to be a little careful, right? If you just naively count, you will not get 7/2.
Yeah, I couldn't get it on top of my head. 7/2. Okay.
You will not get 7/2 if you do naive counting.
Okay.
And then that's one of the subtleties. That is.
Okay.
And so naively, the integral over the bosonic zero modes gives you infinity, and the integral over the fermionic zero modes gives 0.
Yes, exactly.
And it's this 0 times infinity you have to make sense of.
Exactly. That's right.
Okay.
Okay. So what I'm going to do in the next few slides is to just rewrite this again and again in some way. Okay, we are just writing 1 or 0 in different ways. So in the regulated system, okay, we can count the coefficient of e to the minus 2 pi th from the NS sector and separately from the Raman sector. And we get 8 from the Raman-Neveu-Schwarz sector, 8 from the Raman sector. So I've written it as this. Now I'm going to make it, so this is of course 0, right? I mean, as I said, for the next few slides, it's just a 0 that will be written in different ways. So I'm going to rewrite this as 10 minus 2 minus 8. Okay, for a reason that will become clear later. We'll see that these correspond to bosonic zero modes. These are the ghost zero modes, and these will come to the fermion zero modes. So now we are going to use a general result, okay, that if you have an integral like this.
Sorry, Ashok, but once you've regulated, they're not exactly zero modes anymore.
Yeah, they're H modes. I mean,
yeah.
So when I refer to zero modes, okay, we'll refer to modes which have L0 equal to H.
And in this regulated system, the cancellation for H modes looks like it's genuine and correct.
Yes, exactly.
Okay, thank you.
Right? And this is a statement that two D-instantons, okay, separated D-instantons don't have any force, okay, because there is a cancellation between the NS sector and the RR sector in the closed string channel.
Yes.
Yeah. In the open string channel, there is a cancellation between the bosons and fermions. In the closed string channel, it's between NS and RR exchanges.
Yeah. Okay.
So this is a genuine cancellation for separated D-instantons. Okay, so now this is an identity. Okay, if you have an integral like this, we can evaluate it. Okay, in fact, as long as they are equal numbers, the coets are equal, you can just put a small regulated epsilon here, do this integral, and we can show that this is given by this log of this product. Okay. So if you use this formula and use the fact that we have this 10, 2, and 8, okay, we can write n as I times square root of h squared times h to the 8 over h to the 10. Okay, nothing has changed, it's still 1. Okay, so there's no magic over here, but I'm just writing it this way. Now it's again another trivial step. So the claim is that this can now be written as an integral. It's written as an integral over 10 bosonic modes. Then a pair of fermionic modes. These are the ghost modes. We'll see that these actually represent ghosts. And then 16 fermionic modes with this exponent. Okay, and this is an identity. So let's see. So these integrals, this is a Gaussian integral. Okay. In the Euclidean theory, of course, this is just a delta mu nu, contract with delta mu nu. So this Gaussian integral just cancels off this square root of 2 pi. The P and Q integral gives you another factor of h, that's the square root of h squared. Okay, so this gives you 1 over h to the 10, okay, these 10 integrals. And this integral over the 16 fermions, okay, G, okay, I should have said G is a antisymmetric 16 by 16 Hermitian matrix with the property that G square is h times as 16 by 16 identity matrix. This will be like the analog of the Dirac operator, okay, or the zero mode of the Dirac operator in the Raman sector. Okay, that's why you have this G square is related to h. So this gives a Hessian of G, okay, which you can show is h to the square root of h to the 8. Okay, so this is again identity. Okay. So nothing has changed. Okay, everything is finite. It's just an identity that you have written.
And here this infinity and 0 is very apparent. It's this.
Yes,
bosons
exactly.
would go off to infinity and give you this infinity, and yeah.
Exactly. Yeah. So this 1 over h to the 10, right? That will give the infinity, and these are the zeros.
Right. Thank you.
Okay. So now we are going to proceed as follows. So first we are going to show that the integral representation of n may be interpreted as Siegel-Gauge fixed path integral of an appropriate open string field theory with appropriate normalization. Okay. So in fact, you could have said that I could have just forgotten about the world sheet altogether, okay, and started with open string field theory and calculated the path integral. What we have gained from this worldsheet theory is this normalization. Okay, there is no ambiguity in normalization here, right? This is the representation of the worldsheet exponential A, okay? And it is indeed 1 in single gauge, right? That's what the annulus is telling us, that you should get 1 in the result should be 1, at least in the regulated system. So there is no ambiguity to normalization. Okay? This overall normalization you couldn't have gotten if you just started with string field theory, because in any quantum field theory, the overall normalization is ambiguous.
I see.
You could, in principle, I mean, do a few tricks to get this from string field theory, but let me not get into that. Okay, it's basically the same result at the end. Okay, so then we'll show that in this interpretation, the modes P and Q that we see are the Fadeev of ghosts in the Nebel-Schwarz sector. And so this means that in the age goes to 0 limit, you see, in the age goes to 0 limit, this coefficient goes to 0, right? That means that the Fadeev of ghost determinant is vanishing. So vanishing of the Fadeev of ghost determinant is an indication that the gauge choice is breaking down. So that's the first observation, that as you take h to 0, right, that's showing that there's one thing going wrong, okay, which is that the gauge choice is breaking down. So you have to somehow gauge unfix the theory. Okay, you cannot just work with this system. So remedy will be to work with the original gauge invariant path integral before gauge fixing. Okay, where you write this as an integral over the full set of fields, okay, not the gauge fixed fields, and divide by the volume of the gauge group. Okay, so that's the way you rewrite this path integral.
This is in string field theory. You will write it like
in string field theory. But okay, in this case, string field theory will just consist of a few integrals. Okay, normal just 0-dimensional integrals. Because the point is open strings on D-instanton do not carry any momentum. Okay? So unlike normal fields, right, which are position dependent, right? Or in the Fourier transform, it's a momentum dependent, depends on the continuous momentum variable. The string field, the open string field theory on the D-instanton is basically a collection of variables, right? And because you are allowed to throw the L0 larger than 0 modes, it will boil down to doing an integral over only a finite set of variables. So if you don't get too scared about string field theory, we'll write down the string field theory explicitly. Yeah, but that's the strategy.
Thank you.
So you're basically, once you identify this, okay, as a single gauge fixed path integral, you are going to go back to the original path integral before gauge fixing. So this is going to get rid of the 0 modes, P and Q from the integral. Then up to normalization, okay, after that, the 0 modes are easily interpretable. Okay, up to normalization, the mode xi mu, these will represent the translation modes of the D-instanton in the age goes to 0 limit. Okay. So these are the ones which are ultimately going to restore this momentum conserving delta function. Okay, I think this is what Gautam was asking at the beginning. Okay, what about the integration of the coordinate of the D-plane, the D-instanton, that will be here. Okay, so you see that these xi mu integrals are actually hidden in the original annulus partition function, right? Because it's part of the xi mu integrals which are responsible for this h to the 10. But here the xi mu's integrals have to be done carefully. And similarly, these chi alpha modes will represent the fermionic collective modes of a D-instanton in the age goes to 0 limit. And I think to come back to Mithur's question as to the naive G-string counting didn't work, and that basically has to do with this fact that these modes have to be treated separately. Okay, you just can't count the GS associated with these in the standard way. Yeah, and that's what will give this 7 half.
So Ashok, I have what's probably a very stupid question. In your annulus, you don't have any insertions of vertex operators.
That's right, yes.
So when you're doing the annulus partition function, there's no momentum conservation. I thought that would be, I mean, there's no vertex operators whose momentum has to be conserved.
But still, the strings that are propagating are the ones that live on the D-instanton.
Yes.
On the boundary,
yes,
the D-instanton boundary condition, right?
Yes.
So those strings do not carry momentum.
Yes, that's correct. But I was thinking, sorry, I misunderstood you, but I thought you said that this integral would reproduce the momentum conservation of the graviton vertex operators.
Yes, indeed.
And that works even though the vertex operators are themselves not inserted.
Yeah. So the point, this integral, the collective mode integrals have to be done at the very end. After you put everything together. Right?
I see.
So the idea is once
them and do them right. Fine.
Yeah.
Thank you.
So once the collective modes have been isolated, right? Then you have to first do this whole product and then do the collective mode integral.
Yeah, that's not what we normally do in string perturbation theory.
No, that's not how you normally do in string perturbation theory, because normal string perturbation theory works, right? I mean, okay, you can say that's what you normally do in string perturbation theory, but you don't think about it, right? Because if you think of string perturbation theory from the point of view of string field theory, you do one integral weighted by 2 to the s and then product of vertex operators. Right. Is that when you translate it to the worldsheet language, it automatically comes out, right, without any subtlety. That there is separate momentum conservation on each worldsheet.
Right. Sorry, what I was saying was that if you have a product of a disk and an annulus, what that normally means is the partition function on the disk times the partition function on the annulus as a CFT partition. I mean, CFT path integral separately, right?
Yes. But from the point of view of the target space path integral, string field theory path integral,
right?
There is only one integral. Right. And that's what we are doing here. We are reinterpreting this as a path integral in string field theory.
Right. So, but from the normal, so you're not doing the full partition function on the annulus. You're not doing the integral over some of the modes.
Yes, exactly.
Wait and do them all at the end, and that's a bit unusual, but it's the correct procedure. Yes. It's a bit unusual because you would normally have done the zero mode integral of the annulus separately from that of the disks, right? Because those partition functions would just have been independent objects at the worldsheet level.
At the worldsheet level, but these zero modes are zero modes from target space level, not at the worldsheet level.
But they were also worldsheet fields, and they were part of the worldsheet partition.
Xi-mus are not worldsheet fields, right?
What? Sorry.
Xi-mus.
But there were open string modes corresponding to Xi-mu.
Yeah, open string mode, but worldsheet fields means X-mus, right? Which is a function of sigma and tau.
Right.
See, from the worldsheet perspective, these are fixed numbers, right? You fix the D-instanton at one position.
Right, but there was a mode corresponding to the zero mode, which was giving you the trouble for the annulus partition function, right? The thing that naively gave you the infinity.
But that mode is not really a zero mode on the worldsheet.
But then why did it give you infinity from the point of view of the worldsheet? Sorry to keep.
Yeah, at fixed T it doesn't, right?
At fixed H, you're saying. At fixed
T. See, when you look at from the worldsheet.
Right? Now I understand. It's the T integral. Yes.
The T integral which is given the divergence.
Okay, I understand now. Thank you.
Because if there is a problem with the, I think I went the wrong way. If there is a problem with the worldsheet zero mode, then at fixed T you will have a problem.
Right. Okay, thank you.
That's certainly not there.
Okay, thank you. I misunderstood. Thank you.
Okay. Any other question?
So sorry not to slow you down any further, but just to understand, in string field theory, the situation is, can I say the situation is a little bit like ordinary field theory in that you have one integral, say, over the momenta. But now if you look at a particular process where you have two disconnected diagrams, automatically that will break up into separate momentum.
Exactly. Yeah.
That is, but you conceptually you're doing one integral and then for the
exactly. It's like string field theory is like normal quantum field theory, right? And just like a normal quantum field theory, disconnected diagrams have separate momentum conservation.
Right.
In string field theory, also disconnected diagrams will have separate momentum conservation.
Okay. But not here, as you say, here you have to add everything, then do it at the end.
That's right, yeah.
Okay, I got it. Okay, thank you.
Hi, Ashoke. I had a quick
yes.
doubt. So, are you saying that the first quantized formalism gives you the wrong answer somehow? That if you just do naive worldsheet?
Yeah. First quantized answer will formalism will give you 1 for n. Right.
So is this a feature of the D-instanton amplitudes alone, or are there other? I'm not able to understand. What is the set?
I think for D-instanton is the most severe one.
Okay.
Even for many other things, right? You may have to do collective modes, right? Not for the partition function, but for other things, right? For example, the D0 brane recoil is one issue that you get infrared divergences when you try to do perturbation theory in the presence of D-instanton D0 branes. And that's because you are thinking of from the worldsheet viewpoint, the D0 branes are thought of as fixed objects, right? and you
Yes.
are scattering off the D0 branes.
Yeah.
But that is true if you, that's a valid assumption if it was an extended D brane, right? D string onwards, it's okay. But D0 brane actually gets a momentum kick.
I see.
And if you don't take that into account, right, you will get divergences.
Thank you.
So for low dimensional D branes, this is a problem. Right? This is infrared divergence on the worldsheet.
Okay, thanks.
But D-instanton certainly is the most severe, right? Because there's a momentum to momentum. So K equal to 0 really is divergent.
Sorry, Ashok, and just to make sure I'm understanding, actually the reason there was no worldsheet zero mode was precisely because it was a D-instanton. That is the Dirichlet boundary conditions on all.
Exactly.
In all directions.
Yeah.
Had there been some Neumann boundary conditions, then you would have had naive zero modes, but those would then have been weighted with momentum, and that would have been.
Right. That's right.
Yeah. Thank you.
Yeah. Okay, so I think this is what I've already said, that so eventually we'll integrate the collective modes. But in that process, we'll basically have to relate the collective modes to the correctly normalized modes. Okay, and that will generate extra factor in the measure. Okay, so now I'm going to give more technical details. Okay, so let me try to go through it reasonably slowly. Maybe I have only 15 minutes according to official time, I guess. Or
Ashok, you can take as long as you want.
Yeah, I'm going to take as long as you want. I'm going to finish very soon. Okay. So this is the worldsheet description. One quick one-page summary of worldsheet theory of type 2B string. We have the scalars x mu, okay. And then the holomorphic sector contains the fermions. Okay, then anti-commuting ghosts, which are PC, commuting ghosts, which are the beta gamma system, okay. And we can bosonize or fermionize the beta gamma system, okay, by trading in beta and gamma for a scalar phi and a pair of fermions eta and psi. Okay. And exactly similar structure is present in the anti-holomorphic sector. So we define picture number, okay, as q for this e to the q phi. So phi basically is a so picture number is roughly the phi momentum. Okay. But you also assign 1 for xi and -1 for eta, okay, and that ensures that beta and gamma don't carry any picture number. Right? That's as a definition. And then you also have ghost number. Okay, we define 1 for c gamma and eta and -1 for b beta and psi. And for the anti-holomorphic sector, it's the same assignment. Okay, so for example, the picture number for e to the q phi bar will be still q. Okay, for xi bar and eta bar, it will still be 1 and -1. And similarly for the ghost number, right? C bar, for example, will still carry ghost number 1. So the details are not important, but I may refer back to some of these later. So in terms of this, we define the matter stress tensor, which is here. This is the supersymmetric partner of the matter stress tensor, TF. Then you have the BC contribution to the stress tensor and the beta gamma contribution. We have the BRST charge that's defined here. Okay, all in terms of the worldsheet fields. And finally, these are two important operators, the picture changing operator, which is given here, and the inverse picture changing operators. Normally we don't use it, okay, but we will see that it plays a useful role for this particular problem. Okay, in fact, it simplifies things a lot for open string field theory, okay, which is given here. And it's called inverse picture changing operator because one of the properties is that if you take the product of y with x, then it's a non-singular operator product and it just gives you 1. Okay, so y of z times x of z is just 1. Okay, that's why it's called inverse picture changing operator.
So is this factor of 2 normal in PCOs?
No, it's not normal, but it's useful, right? I mean, and the point is, so the fields that have introduced here are slightly different normalization from Polchinski's convention. If you go back to Polchinski's convention, then this factor of 2 will go away.
Okay, thank you.
Okay, but yeah, it's not normal, but it's okay. It's not a. I mean, it just makes things a little simpler. Okay, in this notation.
What did you say, Ashok? Just because I'm not familiar, the OPE of the inverse PCO with PCO is the identity, is it?
It's just 1. Yeah, it's just 1.
Okay.
I mean, there is no singularity. Okay, and the coefficient of the z to the 0 term is just 1.
I see. Okay.
Okay, so here are the mode expansions of various fields. Okay, these coefficients basically reflect the conformal weights of the corresponding field. So for example, this 2 represents the fact that the B has conformal weight 2. Okay, this has, so C has conformal weight -1. That's why this is +1 and so on. And so these are the elementary field mode expansion, and the other two things I'll need are the mode expansion of the total energy momentum tensor, okay, which is here. So ln by definition is the mode expansion of the total energy momentum tensor, and GNM is the mode expansion of the matter energy momentum tensor. Okay, that's the definition, and we also need the mode expansion for Y, okay, which is given here, right? Y has conformal dimension 0, so it's just Y and Z to the minus, and that's the expansion. Anyway, I'm not expecting to remember this, but we may refer to some of these later. And finally, you also have to introduce spin fields, because the Ramon sector vortex operators involve spin fields, which are denoted by S alpha, where alpha will be a 16-component SO901 spinor index. And we define the Ramon vacuum with picture number -half by this symbol. Okay, it's labeled by this index alpha, the spinor index. And in terms of the conformal field theory operators, it's just e to the -5/2 times S alpha 0 acting on the SL2R invariant vacuum. Okay, so that's the definition of the Ramon vacuum. And we'll be working with GSO projected states. So in both the Nebel-Schwarz and Ramon sector, GSO projection basically removes half of the states with wrong worldsheet formula. So later on, we'll list some of the states in this Nebel-Schwarz and Ramon sector, and it will be understood that I'm going to only list states that are GSO even. Okay, so I'll not even talk about GSO odd states when I make that list. Okay, this may be a little quick, but as I said, we'll not need most of it. I'll just refer to some of these things later. So now I come to some details on open string field theory. So here, this is something I already said, I think, in answer to Sandeep's question, that because open strings on D-instantons do not carry any continuous momentum, the string fields are zero-dimensional fields, okay, which means it's really a collection of discrete set of variables. So in particular, the classical Nebel-Schwarz sector string field is an arbitrary state of ghost number 1 and picture number -1. Okay, that's the way the open string fields are. So this in particular means that, let's suppose that you have a basis states. Okay, suppose you introduce a set of basis states UR, and so given any arbitrary state in the Nebel-Schwarz sector, we can expand it in this basis. Okay, and again, I'm talking about only basis of GSO invariant, GSO even states. So phi NS has an expansion of this kind. And when I say that the classical NS sector string field is an arbitrary state of host number 1, picture number -1, what I mean precisely is that it's these expansion coefficients phi r that represent the dynamical degrees of freedom. Okay, so when you carry out the path integral over open string fields, is the integral over the phi r's. Okay, in this case, the path integral is this ordinary integral over this set of variables phi r. And a similar structure also exists in the Ramon sector. So the classical Ramon sector string field is an arbitrary state phi r of host number 1 and picture number -half. Okay, again, we expand it in a complete set of bases, and the coefficients of expansion are the dynamical fields. The only other thing you have to remember is that Ramon sector string fields are Grassmann odd, whereas the Nebel-Schwarz sector string fields are Grassmann even. So given the string that once I've established what the dynamical variables are, the next thing to do will be to find the action. Right? We write down the action for the string fields. And here, because we'll be interested in analyzing the zero mode contribution, we can simply integrate out all the positive modes, L0 larger than 0 modes, and write down an effective action for the L0 equal to 0 modes only. And so these L0 equal to 0 modes basically will correspond to the L0 equal to H modes of the regulated theory, right? Remember that we regulated the theory by this H. Okay, so far you have not taken H goes to 0 limit. Okay, we'll do it soon. Okay. So whenever I refer to L0 equal to 0 modes, I mean L0 equal to H modes. So now we can write down the string field theory action. Okay, and that has this simple structure. In fact, we will mostly need the quadratic part. okay, because you are trying to calculate the one loop determinant, essentially, the annulus partition function. But there are also interaction terms in this. And here we see this Y0 appearing. Y0, let me remind you, is the zero mode in the expansion of the inverse picture changing operator. Normally, the string field theory in the Ramon sector is very complicated. Okay, in fact, you cannot write down simple kinetic terms like this. And the reason is that if you write down a kinetic term of this kind, this Y0 has lots of current. Its kernel is non-trivial. Okay, so when you look at the solution to equations of motion, you will get many more apparent physical states, okay, because those are annihilated by Y0, which are not physical. We know from string, from the world sheet perspective, those are not considered physical states. But if you just take this action, okay, you will get a lot more physical solutions to linearized equations. But this problem is not present in the zero mode sector. Okay, that's why for once you have integrated out the L0 larger than zero modes, and just focus on the ground state, okay, this is a nice action that you can work with. So this basically means that you take the expansion of phi ns, okay, that I gave here, substitute in that expression, okay, you will get some function of the phi r expansion coefficients, and that is by definition the action of string field.
Sorry, Ashok, I missed what Y0 was, please.
Oh, Y0 was the zero mode of the inverse picture changing operator in this expansion.
Thank you.
And so what I was saying is that this Y0, okay, normally is not something that one uses in the kinetic term because it has a lot of additional zero mode and additional zero eigenstates.
Yes.
So those will correspond to solutions to equations of motion if we use this kinetic term. Okay, and now the string field theory gauge transformation parameters. This action has gauge invariance, and this is taken to be an arbitrary state. I think I said somewhere ghost number 1, right? That yeah. So the string fields both carry ghost number 1, right? NS sector as well as the Ramon sector, the string fields carry ghost number 1. String field theory gauge transformation parameters in the same spirit are taken to be arbitrary state of ghost number 0 and picture number -1. And the gauge transformation laws take this form. Okay, so this is the linearized version of the gauge transformation law, and then there are nonlinear corrections, which at least for time being we don't need.
In the string field theory action, you want individual terms to have -1 picture number. Is that right?
Well, not individual. See, the string field theory action, the individual terms, of course, there's numbers. Okay, but phi ns, when we do this expansion, the classical NS sector string field is an arbitrary state of ghost number 1 and picture number -1, which basically means that when you choose this basis of states, in this basis of states, you only include the ghost number 1 and picture number -1 states. And then each of those coefficients is an appropriate degrees of freedom of the string field.
Right.
Yeah, that's what it says. But ultimately, the string field theory action is just a number. Yeah.
Yeah. Yes. Thanks.
Okay. So in the next slide, I think I'm going to explicitly write down, okay, these basis of states. I think that it may become a little more clear. Okay. So here I have listed all the L0 equal to 0 states with the correct picture number, which was -1 in the NS sector and -1/2 in the Ramon sector. Okay. And I have listed them in the order of increasing ghost number. Okay. So this is a state in the NS sector of ghost number 0. That's the lowest ghost number state. These states are ghost number 1. Okay. This is ghost number 2 and this is ghost number 3. Okay. In fact, we will not need these states directly right now. And in the Ramon sector, okay, there are states of all ghost numbers, okay, because it's of the form gamma 0 to the n C1 on this. Okay. And because gamma 0 is a bosonic zero mode, okay, you can apply as many times as you want. Okay. So there are infinite number of states in the Ramon sector, okay, but they have increasing ghost number. Okay, so it will not really affect what you want to do. Okay. So now we can write down the most general form of the string in Nebel-Schwarz sector string field, right? Because you have to take these basis states and write down a general expansion of phi ns in these basis states. And here is the expansion. Okay, this factor of I is just, I have included it because this is what follows from the reality condition on the string fields, but this is not going to be very important. at the end. But with this I, okay, the real string field corresponds to real phi 1. Okay. But the main point here is that you see that you take, this is a basis state, you multiply by an arbitrary coefficient phi 1, this is the basis state, 10 basis states, you multiply by arbitrary coefficient xi mu. And so the string field in the NS sector are this collection of variables phi 1 and xi mu. Similarly, in the Ramon sector, okay, we have only.
Sorry, Ashok, the state -1, the one thing you're acting with your betas and C's on, that's a state that's annihilated by what, B0 or something like that?
Yeah, it's annihilated by B0. So by -1 definition is e to the minus phi on 0 at 0 acting on the vacuum.
Yes.
That's why I defined the Q vacuum. Right? E to the Q phi at 0 acting on the vacuum. And this is indeed annihilated by B0.
Okay, thank you. Thank you.
Okay, in fact, it's annihilated by B0 and beta 0.
Thank
okay,
you.
So you can't go down.
Yeah.
Okay, beta 0. Sorry, minus half is annihilated by beta 0. These beta, of course, half integer here. So otherwise, the properties are the standard properties, right? The positive ones annihilate it, negative ones create something.
Okay, thank you.
Okay, so now we can calculate the gauge transformation. All right, gauge transformation parameter, you can see from here, the Ramon sector doesn't have any ghost number 0 state, right? Because it's ghost number n plus 1 and n starts from 0 onwards. So Ramon sector has no gauge transformation parameter. Okay, so there's no gauge invariance in this. For L0 equal to 0, there's no gauge invariance in the Ramon sector. Nebuchadnezzar sector has one gauge transformation parameter because there's only one state of ghost number 0. So the gauge transformation parameter is just theta times this. Okay, again, this factor of I have included because of a reality condition. We'll see that this is useful. And now using this, we can calculate explicitly the transformation laws of phi 1 and xi mu, right? The way we do it is, remember that the general transformation law is delta phi ns is equal to q beta on theta ns, right? Here. So you first apply QB on theta ns, right? That gives you QB on this. Okay, that's this part. QB on beta minus half C1 on minus 1. And then we project out the component along phi 1, right? You see in the expansion, phi 1 is multiplied by this. So you have to multiply by its conjugate state to project it out. Okay? And that's this. So you can explicitly calculate what delta phi 1 is and what delta xi mu is. Okay? These are the gauge transformation laws. So in terms of this, everything is very explicit. Okay, you can explicitly write down the transformation laws of all the fields. You know that there is only one gauge transformation parameter in the NS sector, 11 fields in the NS sector, 1 from phi 1, 10 from here. And in the Ramon sector, there are 16 formulas. Okay, I think I'll go ahead. So now that we have all the fields, okay, we now define the gauge invariant partition function. Okay, so this is the usual definition of gauge invariant partition function. We integrate over the modes, okay, both the bosonic and harmonic modes weighted by to the minus s, okay, and divide by the volume of the gauge group. Okay, that's the standard definition. Now here, the overall normalization is arbitrary. Okay, I could have put a constant c at the end, it doesn't matter. Okay, it will just drop out. Okay, I have this, so this you can take as a definition of what we mean by I. So what we are going to do now is to gauge fix it in the Siegel gauge. Okay. As I have been discussing, Siegel gauge will turn out to be singular. Okay, but you want to gauge fix it because you want to see the connection to what we had earlier. Okay, because you want to interpret the earlier object, right? That n is what you want to calculate. Right? You don't want to calculate this. We want to relate that earlier object n to this I somehow. Okay, and to do that, you have to go via the Siegel gauge fixing. Okay. So the Siegel gauge is B0 on phi ns equal to 0. So if we apply B0 on phi ns, you see that this is phi ns, right? So if you apply B0 on this, okay, this term is automatically 0, okay, because B0 acting on this is 0. This is not automatically 0, okay, because B0 C0 commutator picks up a 1, or anti-commutator picks up a 1. So B0 on phi ns will be proportional to phi 1. So I'm imposing Siegel gauge means that we are setting phi 1 equal to 0. Okay, that's the Siegel gauge condition for this open string fields. And then this also tells you immediately what the determinant is, right? This is a gauge determinant because delta phi 1 is theta times this. So this is what I've said. So this is a Faddeev determinant. Okay, once you set the phi 1 equal to 0 gauge.
Ashok, in this expression for the identity, shouldn't you have had some delta function corresponding to the gauge fixing slice?
No. Here I have, this is a gauge invariant partition function.
Sorry.
Right?
Oh, okay.
I'm going to do the gauge fixing. Delta function in this case will be just delta phi 1, right? I'm setting phi 1 equal to 0.
Got it.
So I'll just remove the phi 1 integral from this and put in the Fourier-Popov determinant.
Oh,
and then the integral d theta will go away from the geometry. Okay, so but before I do that, I want to write this as a in terms of the Fourier-Popov ghost integral. Okay, so this is a Fourier-Popov determinant which you want to multiply the path integrand by, right? But the way we will represent is where we will introduce a pair of Grassmann odd ghost fields P and Q. Okay, write phi ghost as this. Okay, so this you can see that this is the ghost number 0, this is ghost number 2. Okay, so you have gone beyond what the original string, classical string fields were. And then we write down an action like this. Okay, and you can easily convince yourself that this action, okay, I have in fact chosen these states in such a way that this action is exactly what corresponds to the Fourier-Popov determinant, right? So basically, I have multiplied Q by this state and P by this state. Okay, so that's when you calculate the matrix element of Q between these two phi ghosts, you get exactly this. There is no Q square or P square term because by ghost number conservation they vanish. Okay, you need total ghost number 3 to get a non-zero matrix element. And because of this structure, the integral dp dq times e to the minus s ghost gives us exactly the Fourier-Popov determinant. Okay. So essentially, then what we have done is that we remove this phi 1 integral. Okay. We remove this division by d theta. We introduce a pq integral, and you introduce e to the minus s ghost. Right? That's all that it amounts to. But now let's just analyze the gauge fixed action a little more carefully. So here is a gauge fixed action. Okay, the phi ns qb phi ns. Okay, and then this is a Ramon sector. Ramon sector, of course, sorry, this should have been phi r. Ramon sector, there is no gauge fixing, right? This is the original gauge invariant action. This is the gauge fixing term, the Fourier-Popov ghost term. Okay. And it should be understood that the phi 1 integral is dropped now. But what one finds in the Siegel gauge, okay, because this phi ns now satisfies a b0 on phi ns equal to 0, Ramon sector of course automatically satisfies b0 on phi r equal to 0. This action now takes a simple form, which is given here. Okay. So basically QB reduces to L0, C0, L0 in this sector. Okay. And so this matrix element basically picks up the L0 eigenvalue, okay, which is H. Okay. So this becomes half times H xi mu, this becomes HPQ, and this becomes half G alpha beta chi beta. So what is G alpha beta? G alpha beta is essentially the matrix element of this G0M, the matter superstress tensor, the zero mode of the matter superstress tensor between these alpha and beta states. And one can show that G square is indeed H times 16 by 16 identity matrix. Okay, this just follows from the algebra of these G0Ms. So we are now going to write this, use this form of the action, okay, and rewrite the original path integral in the gauge fixed form.
Ashok, when you acted with B0 on the general field, the condition that set phi 1 to 0, was the variation proportional to phi 1 times H?
Was the variation proportional to phi 1 times H? Yes, indeed. Indeed.
So that's why that gauge fixing doesn't work when H is
exactly, right? So in fact, this is the matrix element is this one, right? And this matrix element is proportional to H. These are for the ghost determinant.
Right. Okay. Yes. Thank you.
Vanishes, and that's why the gauge fixing doesn't work.
Okay. Thank you.
Okay. In fact, I mean, you consider nothing transforms on the theta, right? So there is no need to gauge fix because it's not a gauge symmetry anymore when H is 0. Okay, I mean, it's a gauge symmetry, but it doesn't act on the fields. Okay, and we'll see the physical interpretation of this gauge symmetry in a few minutes.
Could I ask a question? Quick question.
Yes, go ahead, please.
is in the interaction term, like the phi cube, I mean the cubic term in the action, is that also proportional to h? I know you don't need to write it here, but suppose I were to write it down, would it be proportional to h?
Yeah, after an appropriate redefinition, it will be proportional to h.
I see.
And I'll give the argument, right? We'll see that I identify what this gauge transformation really is, and then you'll see that it doesn't transform anything on the worksheet.
Okay, thank you.
Okay, so then with this, the partition function in the gauge fixed formalism, the partition function I becomes, now you have the integral over the gauge fixed modes. Okay, so the xi mu's are of course gauge invariant. We have the Fourier ghosts, dp dq, and then we have this chi alpha variables. Okay? And the action is exactly this, what we wrote down, right? This is the action, and I have just written e to the minus s. And now we'll recognize that this is exactly the expression for n that we had found, except for this factor of 2 pi to the minus 5 and I. Right? Maybe I can go back to the expression for n. Here, right? This 2 pi to the minus 5 is coming from here. Okay, and there is I. Other than this, is exactly the integral that we had to begin with. Okay, so this is what I said. And now you also see that as h goes to 0, the ghost action vanishes. And Siraj just pointed out that this is happening because delta phi 1 is 0. Right? Because this phi 1 actually doesn't transform under theta. Okay, that's why the ghost action vanishes. So this is saying that the Siegel gauge choice is breaking down. Okay, so if we want to take the h goes to 0 limit here, okay, we cannot do it at this in this form. Okay, because this is not the wrong. This is the wrong expression. So the remedy is that we use the original gauge invariant definition of the partition function, which is that you put back the phi 1 integral, and you put back the division by integral d theta, forget about p and q and the ghost action. Okay, that's this one. Except that by going through this process, what you have found is that you have found this explicit normalization factor of 2 pi to the minus 5 that we had. So now in this form, this gives an explicit expression for n that we can deal with. Okay, and that's what we are going to do now. Is this clear? Are there questions? Okay, so you have to now try to carry out this integral. So now evaluate the action S again. Okay, and this time I'm going to take h goes to 0 limit. So in the h goes to 0 limit, as we have seen already, okay, that the xi mu dependence should drop out, chi alpha dependence should drop out, okay, because the g alpha square was proportional to h, right? The xi mu kinetic term was proportional to h, right? H xi mu xi mu. So there is no xi mu dependence or chi alpha dependence, but it turns out there is indeed a phi 1 dependence. Okay, when you actually evaluate this, QB is a known operator. Okay? So you just evaluate this matrix element, and it just gives you 1/4 phi 1 square. Okay? So substitute in S 1/4 phi 1 square. Okay? So at least we can do the phi 1 integral now. This is a Gaussian integral, and we arrive at a result like this. Okay? So these are now the collective modes. Okay, these will be identified as the collective modes after some normalization. Okay? So these will be done at the end. Okay, and we'll see how to do this. Okay? But first, let's try to analyze the xi mu integral, right? What to do with the xi mu integrals? Okay? I've already said that these are related to the location of the instanton in space time. So xi mu should be proportional to x mu with some appropriate proportionality constant. Okay? So now the task is to first find that proportionality constant, because we don't want to lose any constant, right? Because that's what we are after. We want a constant. Okay? So you have to first find the relationship between the xi mu's and the x mu's. Okay? And then we'll rewrite xi mu integral in terms of x mu, picking up whatever measure you get on the way. Okay? And the x mu integral will eventually impose this, give us back the 2 pi to the 10 delta 10 p factor. Okay, but first you have to find xi mu in terms of x mu.
So Ashok, this part of this thing, the relation between xi mu and x mu, This is similar to the 2D analysis?
Yes, similar to the 2D analysis, exactly. Okay, and then this will also be similar to the 2D analysis. So let me give the principle. Okay. So what we do is we calculate a disk amplitude, okay, with some closed string insertions. Okay, closed strings of course can carry momentum. Okay. And one insertion of xi-mu vortex operator. Okay, and the xi-mu vortex operator with this normalization is given here. Okay, so you put an explicit factor of xi-mu, okay, with the vacuum expectation value of xi. Then this is the open string coupling constant. Okay, this has some specific relation to G string that I'll mention later. Okay, but roughly this is some constant times square root of G string. Okay. And then this is the vortex operator. This is the integrated vortex operator at the boundary. Okay, with the normalized, correct normalized xi-mu is this. Okay. So when you integrate this along the boundary, okay, we can basically what happens is you can look at you can use the operator product expansion between the del x mu's and the momentum factors e to the IP dot x to pick up appropriate residues at those points, okay, the poles. So the insertion of this, okay, basically reduces to a multiplicative factor like this. Okay, it gives a multiplicative factor like this times the original amplitude. Okay, and this follows just from the OP of del x with the e to the IP dot x factors. Okay, with this correct normalization. Okay. And then the integral dz, this integral can be done by closing the contour. Okay. It gives a factor of 2 pi i. Okay. And at the end, we arrive at this relation. So this gives the coupling of xi-mu to a disk amplitude with a set of closed strings. Now you can ask, how does an amplitude, okay, with a set of closed strings inserted on the disk, okay, and now the D-instanton placed at the point x, how does it depend on x? Okay. And that answer is simple. It just gives you to the I x dot sum over pi, right? Because x is the conjugate variable to p after all. So if you place the D-instanton at a point x, okay, and insert this e to the IP dot x in the interior, you just pick up a factor of e to the ix dot sum over pi. And so if you expand this in part series in x, you get 1 plus ix times sum over pi and so on. And so now the idea is that you just compare the coupling of xi-mu with the rest of with the disk amplitude and the x with the disk amplitude and read out the relationship between xi and x. So this gives you this combination g open times xi-mu times pi root 2 is equal to x mu. Okay, so that fixes xi-mu in terms of x mu. And that means that when you have this integral over xi-mu, you convert it to the integral over the x mu's with this measure factor. Okay, so that gives you part of the gs to the 3/7 that you saw. Okay, part of that will be from here.
Sorry, Ashok, you are multiplying xi-mu with del x mu and so on. What happens to del bar? Isn't there some del bar x mu kind of or not?
Yeah, so these are the boundary. These are open string vortex operators, right?
Yeah. Okay.
So they are the del x mu and del bar x mu are related. Yeah. Inside, of course, you can have other vortex operators, right? But that you don't care about because you are just looking at the residues, right? It just picks up the p over z minus zi factors.
So Ashok, if we were not interested in the pi and square root 2, but just the G0 dependence, we could have guessed this on general grounds?
Yeah, this we could have guessed from general grounds, right? The only part which is slightly non-trivial is this the theta integral, right? Because if you just naively do this G0 counting, right, you will count that two pair of zero modes from the ghost center,
right?
And you will count one G0 for each,
right?
That's what changes when you take into account the fact that the Siegel gauge is not a correct gauge choice.
Right. Right. But and the square factor of pi and square root 2, could you have guessed that somehow also, or that is too complicated, too detailed?
Well, yeah, that I don't know. I mean, it comes from this comparison, right? I mean,
yes. Okay, thank you.
Yeah, maybe there is a way to guess it, but at least I can't see it immediately. Okay, so with this, I just take out this factor and convert the xi integral into the x integral. So the next task is to figure out what this is, right? This is the integral over the volume of the gauge. Okay, and so now I can explain what this theta gauge transformation really is doing. This, in fact, can be shown to be related to the rigid U1 gauge transformation parameter psi on the D-instanton. So on every D-brane, there's a U1 gauge structure, which typically gives rise to the U1 gauge group, but there's also U1 transformation. And you know that the U1 transformation, in fact, doesn't act on the open strings that begin and end on the same D-brane. This affects open strings that are charged under the gauge field, which means that if you take an open string that starts on a given D-brane and ends on a different D-brane, those transform under this rigid U1, the overall U1. Now on D-instanton, of course, there's no gauge field, but there is still this rigid U1 symmetry. And that's what this theta that we introduced represents. So the rigid U1 gauge transformation parameter I've called psi, and then this theta is the theta that is the open string gauge transformation parameter. And the idea now is that we'll try to change variable from theta to psi. So psi, again, let me define here that if you take an open string that connects the D-instanton to the neighboring instanton, that state picks up a factor of e to the I psi. But if you take an open string that connects the D-instanton to the same D-instanton, then there's no phase. And in fact, this comes back to Onkar's question, right? That could you have gotten any theta dependence in the interaction terms? And the point is that you cannot, because if you just look at the one open string field theory for open strings that begin and end on the same brane, right, is just neutral under the psi transformation. So that means that after appropriate redefinition from theta to psi, right, everything will be psi independent. Okay, but now we want to find a relationship between theta and psi. So what we do is that we compare the infinitesimal transformation by psi, right, which just gives you I psi times the original state. We compare that with the string field theory gauge transformation parameter that is generated by theta. This in fact is known in terms of the star product. So you just take some particular state, see how it transforms under theta, see how it transforms under psi, and then compare. But this state has to be a state that connects a given D-instanton to a spectator D-instanton, right? So you have to bring a spectator D-instanton and then do this comparison. If you take open strings from the D-instanton to the same D-instanton in the original string field theory, then nothing transforms. So this can be done. You compare this and we find that there is a relation between theta and psi of this form. Again, this GO comes because from the open string field theory viewpoint, right, whenever you insert a vertex operator, it is multiplied by GO. Right? That's why this G0 comes. GO comes, and then this 2 is just some details of the calculation. So this allows us to replace this integral d theta by 2 over GO times integral d psi. And now use the fact that from this we can see that psi has period 2 pi. Right? If you change psi by 2 pi, it doesn't transform anything at all. So we replace this integral by 4 pi by 0. Okay, that will give a factor of GO over 4 pi from this theta integral in the denominator.
So Ashok, it's like psi is the gauge parameter and the normalization where there's a 1 over g square outside the action. Whereas theta is the gauge parameter and the normalization where there's 1 outside the action.
Exactly, that's right.
Thank you.
Ashok, so you have 2 D-instantons. So this U1 that you are talking about is the diagonal U1. Is that right? Or
U1 is the diagonal, or the U1 is the U1 on one D-instanton. The first D-instanton. Right?
One D-instanton. I see. Okay.
The spectator is just there to provide the open string that connects the two.
But the open string that you are thinking of is the one that connects one D-instanton to the other one.
Yeah. So the original D-instanton that you are interested in to the spectator.
Yes. Okay. Got it.
So basically, we have to look at the transformation of that particular open string.
Mm-hmm.
And the way it enters the calculation is because there is a Chan pattern factor. And if you just take the open string from the D-instanton, the same D-instanton, right, then 2 cyclic orderings cancel. If you take the open string connecting one D-instanton on the neighboring D-instanton, then only 1 cyclic ordering contributes, and that's what gives this transformation law, right? This G0 times GO times theta by 2, it comes from there.
I see. Okay, thank you.
Okay, So now we have got this N, right? This is more or less the end of the subtle part of the calculation. And now all you have to do is that you have to basically put in the rest of the amplitudes, the disk one-point functions, and integrate over x and phi. Okay. So the x integral that I have already said, this x is now correctly normalized, so it will just generate this factor. The fact that you have this integral over chi's basically says that other worldsheet components must have chi's. Because if you just take the original amplitude that I gave, right, the disk one-point function of 4 gravitons, okay, then the integral over the chi alphas will just make the answer 0, right? Because it's a integral over Grassmann variables without any saturating chi. Okay. So what this is saying is that unless there are 16 insertions of chi alpha in the rest of the amplitude, this integral vanishes. Okay, so I'll make it more specific later. Okay, so basically this means that in this amplitude, we now have to insert 16 chi alphas distributed on these 4 disks. Okay. And the chi alphas are inserted by using the vertex operator. So this is needed. So I have written down here both the unintegrated vertex operator as well as the integrated vertex operator. Okay, this is unintegrated, you just insert it and at a fixed point. Okay, and this is you insert it and then you integrate over the location. Okay. So now, in principle, you could have distributed in different ways, right? You could have put all the 16 on one and none on the others. But what one can show, okay, by this explicit calculation is that if you have a disk amplitude with other 0 insertion of pi or 2 insertions, that amplitude actually vanishes. Okay, just by tensor contraction. Okay. And that means that you really need 4 chi's per disk. Okay, so it have to be uniformly distributed, not just distributed in any way.
Why
So,
sorry, Ashok, sorry, I'm very sorry, I missed part of the last few slides, but why does it have to be uniformly distributed? If it vanishes for 0 and 2, then why can't it
we need 16 chi's altogether.
Oh, okay, sorry. Yeah.
So if it vanishes for 0 and you can have odd number because that's odd number of formulas, right?
Yeah.
So if you need to distribute 16, right, you need 4.
Sorry. Excuse me. Yeah.
Ashok, I'm really sorry, but I missed the logic for these chi's. I mean, why are we inserting chi's on the disks? I understand that you get something 0 otherwise, but what was the reason that the procedure forced us to do that?
Yeah, so the point is that we are trying to calculate this path integral, right? Open string modes will be integrated out at the end because you only have external closed strings. We are interested in closed string 4-point amplitude.
Yes.
Right? And in that process, we have to integrate out the open string modes completely.
Yes.
Okay. So suppose the effective action contains a coupling between 1 closed string and 4 open strings, 4 chi alphas, right?
Yes.
Then that has to be expanded, then the chi have to be integrated.
Okay.
To give a 4-point amplitude, right?
Okay. Okay. Thank you.
If you just take the h to the 4 coupling in the original in the action, that is not what contributes.
I see.
Because chi alpha will give you 0.
Right.
What you need is a coupling of the form h to the 4 times chi to the 16.
Right. So you say that you could have put arbitrary numbers of these chi's, but only this contributes.
Only this contributes.
Okay, thank you.
4 parties.
Yes, thank you.
Is this an index theorem of some sorts?
Not really. Okay, maybe there's an index theorem also, but I mean, if you just calculate the appropriate matrix element and use the fact that eventually this chi alpha, these integrals will be completely antisymmetrized in all the indices, you find that you don't get any non-zero answer for 0 or 2. Okay. For example, if you just insert 2, you get a gamma alpha beta, and gamma alpha beta is not to be symmetric. That makes this 0.
Yeah.
Right? If you don't put anything, then basically the index contraction tells you that you either get something proportional to the trace of the polarization tensor or momentum contract to the polarization tensor, and both of those are 0. Yeah, so it's just mundane observations like this which makes this 0, but maybe there is also an index theorem. That's possible. which tells you that you need precisely 4 per disk. Okay, so now suppose we denote this, okay, the amplitude by A alpha beta gamma delta times of H. Okay, H is linear in H, right? And alpha beta gamma delta, those are the indices carried by the chi's, the 4 chi's, okay, on each disk. Now this is, I'm just talking about now each disk. Then that means that the effective action of open and closed strings will carry an interaction term like this. Okay, 1/4 factorial, because your content, this is the amplitude, right? So the action will contain something like this. And now the idea is that you have to integrate out the chi alpha modes altogether. Okay, so we'll take exponential of this and then integrate out the chi alphas. Okay, and this is what I've done. Okay. So you have the integral over the chi alphas and then exponential. I think there should have been a minus sign here, doesn't matter. We have an exponential of this. And when you evaluate this, you have to basically expand it out to 4th order. So you get 1/4 factorial times 1/4 factorial to the 4 times the epsilons, and then the product of these 4 A's. Okay. So the chi's have gone, right? Because the chi alpha integrals basically produces this epsilon. Okay, epsilon is 16 indices. So that's the amplitude. Okay, this is what we get. So this is the final resultant for the 4 graviton amplitude. What all these normalizations put in, then 1/4 factorial to the 4, this contrasted with the product of the A's. And these can be explicitly computed, right? These are in fact a reasonably straightforward calculation, because we are having 1 graviton insertions and the 4 zero mode insertions on the boundary. Okay. Now the only subtlety here could be that when the zero modes approach each other, okay, there can be singularities. Okay, there can be poles, and you may wonder how to integrate through those poles. But what one finds is the product of the 2 zero modes, okay, chi alpha and chi beta, is the singular part is proportional to gamma mu alpha beta, okay? And gamma mu is symmetric, okay, in this case. And because of the symmetry of gamma mu, okay, once you contract to the epsilon at the end, okay, those terms go away anyway. So there is an ambiguity in doing these integrals, right? There is a singularity in from the collision of the vertex of parts that are integrated on the boundary. Okay, it's a perfectly well-defined integral which you can do and get the answer for A.
Ashok, I'm sorry. Again, I apologize because I stepped out briefly, but the momentum conservation integral is been done already at the stage where you compute A with 4 chi's, or is shouldn't?
Yes, no, here. Yeah. Okay, this I have put in. I didn't have it before, but I have cheated a little bit, right? So this integral I should have written as integral d10k times e to the ik dot x, where x is the location of the d-instanton. Okay, so when you expand this out, okay, you also get this e to the ipi dot x. Okay, because these were accompanied by e to the ipi dot x. Okay. And now we are going to do the d4x integral, right? Because these integrals are left. Remember, this is the these integrals are left. They have to be done at the very end, right? After you multiply this by the rest of the amplitude.
Right. That's what I was trying to. Yeah. So sorry. So you do it after the you get the A and the 4 chi's.
Yes.
And
then you can do the chi integrals first.
Yeah. Okay.
Get the epsilon.
Yes.
And then at the end, you have this product of e to the ipi dot x.
Right.
And then integrate over x.
Okay. But the G zeros are all pulled out before that. Huh?
Yeah, G zeros are pulled out. I mean, some of the G zeros are pulled out here. And some G's are hidden inside the A. Okay, which I'll tell you how to put it out.
Okay. Thank you.
Sorry, Ashok, you have this very beautiful way of getting this KC factor here. Coming from these.
But this was given originally by Green and Gutperle. They didn't calculate the normalization, okay? But they had some argument as to how to get the KC from here.
Okay. Now, just in tree-level type 2 string theory, we also get just for on the sphere scattering, we also get this KC factor. Yes. Is there some similarity between the mechanisms, or I mean, from this technical point of view, can you could you have seen before and you would get the same polarization dependence?
Yeah, I think, okay, the way I know that this, the way this comes, okay, is that this comes as a, so each A is like gamma, suppose the, so each A is characterized some polarization, right? E, and some momentum. So there is a gamma mu nu tau, gamma rho sigma tau contraction. Okay, so gamma mu nu rho has indices alpha beta. Okay, and, the other one has indices gamma delta. Now of this gamma mu nu, one is contracted with a polarization tensor, the other one is contracted with a momentum. Same is true for the second one, right? Because polarization has two indices.
Yes.
That's how this index contraction works, and eventually when you expand it out, you get this Kc. And this kind of structure I have seen in the superfield expansion. That when you do this on-cell superfield, I mean, there are ways to do this on-cell superfield expansion. I mean, there it's exactly this structure which comes. And I think there also the Kc will come out from this identity only. Right? You don't directly get Kc when you try to write in terms of superfield. If you remember this Pedro's talk, for example, right? He was using this delta Q notation for the same amplitude, okay, which is using this on-cell superfield.
Yes.
There, I think if you want to get the Kc factor explicitly, you have to use this identity of this kind.
Okay. So you're saying that the reason that it gives the same is just supersymmetry, basically.
Yeah, exactly.
Okay, thank you.
So, supersymmetry, you already know, I mean, it should force you to have this up to this normalization.
Okay.
Okay, so here is the result taken. So I'll just end. I think this is almost the end, maybe a few more slides. Okay. But let me just now say how to pick out the factors of pi and g. Okay, because the factors of 2 hopefully should work out, but that, as I said, haven't been worked out yet. But pi's and g's I can try to explain. So there are some pi's and g's already explicit here.
Sorry, very, very sorry. Please forgive me, Ashok.
Yes.
But I mean, if you mentioned it, when you first presented the result, there was a wasn't it G0 to some
7 by 3 half.
Yeah, 7 by half.
No, GS to the 7 by 2. Q is like an open string coupling. I'll say how this is related to GS.
Okay. Thank you. You haven't said that. Okay. Thank you.
Okay. So this came from the end. The first part came from the end. Then this is the momentum conserving delta function. Okay. This 2 pi to the 10 is not part of this pi counting. Okay, this is always separate. I'm not counting this in this. And then we have this factor. So we'll count powers of string coupling and pi, right? Because everything here is explicit. Only the A we have to know what it gives. So each A, okay, gives you first of all a factor of 4 GO. Right? Because you have the 4 chi alpha insertion, and 1 kappa, because closed string vortex operator comes with the factor of kappa. Okay, that's the closed string coupling.
So,
then you have.
I'm sorry to interrupt, Ashok. Just in your top line, you had these various powers of G0.
Yes.
The 1 over G0 to the 10 that came from the Zyme. That came from the Zyme.
Yes.
And the next G0 came from the gauge fixing. That gauge parameter.
Yeah, exactly.
Yes. Okay. Thank you.
And then some more is going to come from the chi, right, which are hidden inside A. Okay, and that's this. The GO to the 4, this comes from the chi's.
Thank you. Yes.
So 16 chi's will give GO to the 16.
Yes, thank
you. Okay, so H is the graviton vortex operator that comes to the kappa, right? Okay, kappa is the closed string coupling. Okay. And I wrote down the relation between kappa and GS in the first slide, but I'll do it again. Then from the D-instanton tension, we get a factor of 2 pi by GS, right? That's this GS to the minus the Euler number that I mentioned. That's this 1 over GS. And it comes with this factor of 2 pi. In fact, actual factor is pi, okay, because there's a half, but we are not counting 2 as a 2's anyway. Okay, so this is a pi by GS. And then it turns out that each of the chi alpha insertions gives a factor of pi, okay, or a 2 pi. For 3 of them, it's easy to understand, right? Because the way that this comes is, okay, so this is a disk amplitude with 1 closed string and 4 open string insertions. Now on a disk, we have 3 conformal killing vectors, okay, that's upper half plane. So you can fix the closed string vortex operator position and the open string vortex, one of the open string vortex operator position. Okay. So 3 open string vertex operators are being integrated. Okay. And typically we perform those integrals by closing the contour, okay, picking up residues. Okay. So each of those integrals gives a factor of 2 pi. Okay. Again, I'm leaving out factors of 2 in that process. So that gives you 2 pi cube. Okay. The final 2 pi, in fact, is a little subtle. So that you may wonder that how that comes, because you have a fixed open string vertex operator, right? Okay. So the way it comes is because if you look at just the closed string 1-point function on the disks, right? That's what is calculating the tension. Okay. The closed string 1-point function on the disk has a conformal killing factor. Okay, because this can be rotated about its. So that amplitude calculation has an implicit 1/2 pi. Okay, that has gone into the D string tension, the D-instanton tension calculation. Okay. So when you now insert the open string vertex operator, that 2 pi is gone, right? Because now this doesn't have a conformal killing vector anymore. So you have to put in that factor of 2 pi. Okay, so that's this final factor of 2 pi. You get this 2 pi to the 4. Okay. So now we can count the powers of pi and G string. Okay, so this is, you see, pi to the minus 5, I have written pi to the half. This is pi to the minus 10. Then this 1/pi is here. Then GO to the minus 9 is the minus 10 plus 1. And then everything else is from the A, right? 4 powers of kappa, 16 powers of GO. Okay, because each of these is repeated 4 times. Then pi by GS comes 4 times. And then this pi comes 16 times. Okay, that's the net factor of GO and pi.
Sorry, Ashok, this extra 1/2 pi, this was the fact that there were 3 ghost 0 modes on the disk, but only 2 of them are eaten up by insertion of a closed string vertex.
Exactly, that's right.
Thank you.
So one, and in this case, normally you would say that, okay, in that case, a result should vanish, right? But because you are dividing by the volume of the gauge loop, right? But here it doesn't vanish because it's a finite volume.
Yes. Yes.
And the finite volume is 2 pi.
Yes.
So that you are divided by that in calculating the 1-point function of closed strings. But once you insert an open string, you have to put back that factor, right? You are not dividing by anything now. So that's this last factor of 2 pi. Okay, anyway, so after all this, okay, now here are the relations. This is something that I've already written before. Okay, the relationship between kappa and G string. Okay. Here is a relationship between the GO and G string. Okay, this can be found using the factorization. Okay. And here I should just mention that this relation between G open and G string depends on the particular D-brand we consider. Okay. The GS, of course, is fixed. This is closed string coupling. Okay. But on different D-brands, you have different effective open string coupling. Okay, so normally if you try to compare this with Polchinski's result, for example, right, there the GO is normally referred to as the open string coupling on the D9 brand, right? The space filling D9 brand, because that's where the type 1 string coupling comes in. Okay. But as you change your P on different DP brands, there is a different G on the open string coupling, and for D-instanton, this is a relation. Okay, that you can find.
So GO is defined so that every vertex operator is GO times E to the power whatever.
That's right. GO times the standard normalization vertex operator.
Okay. Yes. Thank you.
Exactly.
Why is this? I'm sorry, you probably explained it. Why does it change like that? The kinetic energy term depends on P, is it? I mean, and then that affects the 2 pi's or why?
Yeah, roughly. I mean, basically, the actual relation is that GO gets directly related to the tension of the brain. And because the 1 over GO square is a fixed multiple, 2 pi square times the tension.
Okay.
But the tension keeps changing, right? By this 2 pi factor.
I see.
And that's why the GO keeps changing by this 2 pi factor.
I see. So 1 upon GO square is related to the tension by some fixed.
It's 2 pi times the tension.
2 pi times the tension. Okay. I see.
Not 2 pi. 2 pi square times the tension.
I see.
Okay. So in this case, it's 2 pi square times 2 pi by GS. Right? That's the 4 pi cube.
Okay. Thank you.
So that's the general rule, right? If you want to know the general rule for calculating GO for a given V-brand, that's the rule.
Yeah, I see. Okay. Thank you.
Okay, so now you just put everything together. And you see that this GS to the 7/2 emerges and pi to the 8 emerges, right? These are exactly what you have from the prediction of S duality. Okay. And as I said, factors of 2 still remain to be checked. okay, in this. So we still don't know if the this analysis gives the correct answer or not, okay, because of this factor of 2.
I see. Ashok, I'm very sorry for this naive question, but and especially because, but isn't the really non-trivial factor of G0 the one which came from the volume of the gauge group?
Yes, indeed.
Huh?
That is the one which you couldn't have counted just from the zero mode counting.
Yeah, it seemed like
Because
that.
you got a volume, the Bose and fermion zero mode counting,
Yeah,
you didn't get that factor.
yeah, that really seemed very non-trivial. Okay, thank you. Thank you.
And that for that, basically, you have to realize that this because of this breakdown of the Siegel gauge, the gauge fixed zero mode counting is not the correct thing to do. Right? You have to really go into the gauge unfixed version.
I see. I see. Okay, thank you.
So to get this factor of the 2 pi's with the G0, we could take the dBi action and then renormalize fields so that all kinetic terms are 1. And that change in normalization gives you this thing.
Yes,
right?
Yeah. That's what I was also thinking. The kinetic terms.
Yeah, but you can also get it. I mean, without going to effective field theory, that's from purely string theory, right? That if you take a given amplitude and factorize in two different ways, right? In one way, you factorize by a closed string channel. In another way, you factorize by open string channel. Once you factor by open string channel, you get some extra factor of GO, right? And then you compare the two.
Yeah.
And that fixes the relationship between the open and the closed string couplings.
Yeah.
Like Polchinski does in his textbook.
Exactly. Yeah.
Yeah.
So there are many ways to fix this.
Yeah.
And always give the same result at the end.
Right. That was your tension comment, right?
Yeah.
Yeah. Okay.
Now there's one final thing that I have to say, okay, and that's this multiplier factor. So what we have described so far, okay, is that this gives a result that the calculation that we did, okay, this gives a result of integration along the steepest descent contour of the instanton, right? And in this case, the steepest descent contour is basically along the real axis. But then you have to ask, how does this steepest descent contour fit in the actual integration contour of over the string fields?
Sorry, Ashok. Again, I apologize, but this is now integration in string field variables.
Yes,
am I right?
In string field variables, exactly. Right.
Okay.
So you carried out these integrals using Gaussian integrals, right?
Yeah.
All the way from -infinity to infinity.
Mm-hmm.
So that's what I mean by saying that you are doing the integration on the steepest descent contours.
Okay. Okay.
Which in this case are all along real axis. Once you, because there's no tachyon, so you do everything along the real axis.
Okay.
But the confusion here, okay, at least it confused me for a while, is that if you look at the Euclidean D-instantons, they are actually complex solutions in supergravity. In particular, the Ramon-Ramon scalar is imaginary for these D-instanton solutions. So if you think of this as an integral over the closed string variables, right? If you think of this as an integral of a path integral over the closed string fields, you may wonder that how come the D-instantons contribute at all, because they are on the off the real axis, right? Normally you would think that the closed string path integrals would be done along the real axis, and the D-instantons are sitting for imaginary values of the closed string fields. So you shouldn't include these in the path integral.
Wait, Ashok, I'm very, very confused. Sorry, please. They are complex solutions in string field theory or super?
No, that's in supergravity. If you try to write down the super, this was done by Green and Gutperle in their first paper.
I see.
If you just try to write down the supergravity solution,
yeah,
with the D-instanton as source, you find that they are complex solutions. The Ramon-Ramon scalar is imaginary.
That axion, huh?
The axion, yes.
It is imaginary. I see, because maybe you're doing you do it in Euclidean 10 dimensions, I guess.
Yes.
To pick up an axion.
That's right.
I see. And then sorry, just a minute. And then repeat your point that because they are complex solutions.
So
imagine
that you think of define the string field theory path integral, or the string theory path integral is over imaginary over real subspace, right? Real fields.
I see.
Then that integration contour is basically going to miss the D-instantons altogether, right?
But isn't this a situation often in saddle point evaluations that you deform the contour to go through a saddle point, or,
Yeah,
or you're
that process typically introduces various multipliers. Because sometimes, well, I think Mithat is the right person if he's still around. That sometimes this saddle point is included, sometimes it doesn't include, depending on how you continue. So,
yeah. So why should it contribute in this?
why should it contribute?
Not
Right? And
obvious.
even if it does contribute, you have to figure out how it goes through, what the multiplier factor is, and so on.
Okay. Okay.
Yeah, one sort of needs to find the Lefschetz symbol.
Yeah, exactly. Yeah. Fortunately, I'm not going to do that. Okay, because that would be really a long story. But and finding Lefschetz symbols for supergravity, I don't know how easy it is. Okay. But I'm going to take a slightly different viewpoint, okay, on these D-instantons. Okay. And here is the viewpoint that if you really want to think of these D-instanton solutions of supergravity, these are actually singular solutions.
Yeah.
Okay. So it's not even clear that even if they are real, whether you should include them or not. So I like to think of this as regular solutions in an unstable D-brane system. Okay, that if we start with an unstable D-brane system, okay, we know that the vacuum of the D-brane defines standard perturbative vacuum. So you could, in principle, set out the path integral, okay, as path integral over both closed strings and open strings, and those open strings live on unstable brane system. So the usual perturbative amplitudes come out automatically, because around the vacuum there are no open string excitations. You only do the closed string part. But the advantage here is that on an unstable D-brane system, the D-instantons, okay, can be regarded as regular classical solutions of open string field theory. So here is an example, right? We can take, for example, a Euclidean non-BPS D0 brane, okay, which is one-dimensional, right? In Euclidean space, it's a D0 brane is a one-dimensional object, and you can think of a D1 brane, sorry, a D-instanton as just a regular kink on a Euclidean non-BPS D0 brane. It has a tachyon, which has, which you can think of this as interpolating between a vacuum and another vacuum, and it's just a regular kink solution. Or if you take an Euclidean D1 bar system, you can think of this D-instanton as a vortex. Okay, again a non-singular vortex solution in this system. Okay. And so if you think of it from this viewpoint, right, you introduce additional open string degrees of freedom, okay, but they don't really contribute at the perturbative level. Okay. Then you can describe these as regular real solutions of this open string field theory. Okay, there is no complex solution. It's not a complex solution. And the reason that from the closed string perspective, it looks like a complex solution comes because the coupling that on the D-instanton, on these D-branes, okay, on non-BPS branes, there are couplings which become complex or imaginary when you do a Euclidean rotation. Okay, they are perfectly real coupling on the in Lorentzian space, okay, but they become imaginary when you weak rotate. Okay. And this is very analogous to Chern-Simons theory, for example. Right? The Chern-Simons action, which is real in Lorentzian theory, right? They become imaginary when you weak rotate, right? Because of the epsilon symbol. Okay. So, for example, if you think of a non-BPS, sorry, this should have been a D0 brane. Okay, if you take a non-BPS D0 brane, and if T is a tachyon that condenses to the whose vacuum describes the usual perturbative vacuum, then you know that there's a coupling of the form chi dt. Okay, on the world volume. If chi is this Ramon scalar and T is open string tachyon. Okay. And you can see from here that once the tachyon condenses, okay, once you get a tachyonic kink, okay, that generates a source for chi. Okay. And in the Euclidean space, okay, this is an imaginary source. Okay. So from this perspective, the reason that we are getting an I when you think of this as a solution in closed string theory is because the action becomes complex in the Euclidean theory, but the actual solution in terms of the open string theory is perfectly real. Okay. And from this perspective, I conclude that the full steepest descent contour should be included. Okay, and this viewpoint, in fact, is also useful in this two-dimensional string theory in deciding what fraction, okay, this open string viewpoint, okay, is useful in deciding what fraction of the contour you should include in the final answer. So based on this argument, I think that there should be no additional multiplier factor, and you should just multiply by 1. Okay. Of course, it could be -1, but that's just a phase, right, which can be absorbed in the axion field, in the vacuum expression value of chi. I see.
Well, sorry, Ashok. There's is the idea that there is a path in string field theory space that passes through the vacuum, which is the place with no d-instantons,
Yes.
and also passes through this d-instanton saddle, just going
No.
up. Okay, sorry.
Okay. That cannot happen because it's a topological defined sector. This is a kink, right? But there's a path which passes through the vacuum and also the kink antiquant pair, which are sufficiently far apart. So just by factorization, you have to include the kink.
I see. I see. And this path is just along the real axis. All
Along the real axis, exactly. Right. From the open string perspective, everything is real. Right. It's that you shouldn't think of this as a solution in closed string theory.
Okay.
That's singular solution anyway. Right. D-instant. I mean, you don't normally think of B-bands as solutions as a regular soliton solutions in closed string theory, right?
Yes. And is it clear that this, even though the saddle points are real, that the path does not have to move off into the complex plane, let's say, after it goes through one of these saddles? I mean, sorry, it's probably a stupid question, but
well, if you take the original integration contour to be completely real,
right,
then this will include all these saddles, right? Now, all the at least the kink anti-kink pair, it should include an arbitrary separation.
Right.
Right. And then by cluster property, you know that the kink has to be included separately.
Right.
Otherwise, the amplitudes will not factorize.
Right. Sorry, I was thinking about your previous talk, your talk at ICTS, where you had a path that went along what looked like a real contour up to a top and then branched off into the complex plane.
Yes.
In that case, also the two saddles were at real values, right?
That's true. But there's a tachyon.
Your path had to go off into the complex plane after hitting the second saddle.
Yeah, because that's because there was a tachyon.
Ah, so yes, I see.
Tachyon forced us to go into the complex plane because the integration along the real axis would have diverged.
Fine.
The only sensible way to choose a contour was by going into the complex plane. Here, you can take the contour, the full integration contour to be completely real. Right?
Right. And there are no other possible choices. Could it be one of these situations where there's some degenerate kind of Lifshitz symbol where you could have had a choice of going off somewhere else? Or this is ruled out?
But it doesn't, I mean, at least this is one choice.
And you say this is what physics gives you?
Yeah. Integral on the real.
Okay, thank you.
Ashok, I'm sorry, I have to apologize to you and everyone because I have not upgraded my skills to include Lifshitz symbols. But can I ask the following? It seems to me you are saying that this thinking about the D-instanton as a solution in closed string supergravity and therefore thinking of it as a complex solution is a bit misleading from the point of view of open string field theory.
That's right. Exactly.
Huh?
Yeah.
And by thinking of it as an unstable system, which then condenses, it becomes manifestly clear that you can think of it as a solution in open string field theory for real fields.
Exactly.
And therefore, now you feel more confident that it was okay to do the integral over just the real fields.
Yeah, exactly. And the full integral. I mean, all the way from -infinity to infinity.
From -infinity to infinity. But, and then just to make sure I understand, you know, the little bit I know about saddle point analysis is that you try to deform your contour so that it lies at constant phase. And if after that it's going through a saddle point, you are pretty confident and you include the full saddle point across both sides. And here, are you saying, look, because you're sure it's a real integral, it's also absolutely clear that it's at constant phase, and then you include the full integral.
Exactly.
Is that what you're saying?
Yeah, that's what I'm saying.
Okay, I got it. Thank you. Okay, thank you.
Maybe a remark about what Sandeep said, that
Okay.
constant phase is really property in the case of one-dimensional integration. So if you consider higher dimensional case, you have to consider the complex gradient flow equation. That's the counterpart of, you know, this constant phase approximation in the one-dimensional
I
case.
see. I see.
And that's the left set symbol, right?
Yeah. So you pick the middle dimensional subspace in a higher dimensional space, but you know, in for one-dimensional example, this just reduces to the constant phase approximation. It's not an approximation actually, constant phase contour.
I see. Mithat, afterwards, I'm going to complain to you. Your famous ICTP lectures are not online in written form. Anyway, afterwards, I ask you, maybe I'm wrong. Okay, I have to learn this. Go ahead. Sorry, Ashok.
Okay.
Okay, yeah, I'm more or less done. This is the last slide. So the conclusion is a string field theory at least seems to give a systematic procedure for computing D-instanton contribution to the amplitudes. Whether it gives the right answer or not, we don't know yet, right? Because factors of 2 haven't been worked out. And once all the details are understood, and if we do manage to get the right answer, then we should be able to apply this procedure for systematically calculating D-instanton contribution to superpotentials in n equal to 1 supersymmetric string compactification. That's the immediate example I can think of application. And presumably there are other problems where D-instanton corrections might be important. Okay, and we could apply these techniques there.
I see.
I think that's about it. Thank you.
Maybe we can unmute and clap. Okay, questions?
May I ask a question, Shiraz?
Of course.
Ashok, just to go to your second red part in the conclusions. I mean, this is very impressive, but just to take type 2B, I mean, as you know, this corner, which is of interest from the point of view of KKLT and so on, just to take type 2B with Ramon fluxes and NS fluxes turned on and so on, you would not be at all intimidated doing doing the superpotential computations in those cases? I mean, how would you, I mean, I would never have the guts to you. I mean, how would you do this? In string field theory, you would do it or what?
Okay, so I mean, I think the point of one is to start from places where one can be reasonably confident of doing it first, right? Which is that take some orbi, for example. See, if you take a generic Calabi-Yau, then you cannot do anything, right?
Right.
I mean, even in normal worldsheet calculation, you cannot do. So you can take, for example, an orbifold and consider the case first where the Ramon fields are small or 0. There you can do the calculation, and then you can try to see if you can correct it by the presence of the Ramon background. Right? But first thing to do it will be to just take a standard orbifold, n equal to 1 supersymmetric, and try to do the calculation of D-instanton.
And you're saying already, because the overall normalization certainly is not known from any cybergology or souped up versions, this would be very interesting.
Yeah.
I see. Okay. Yeah. Okay. Very interesting. Thank you.
More questions?
Yeah, Ashok, so this is not about 10D, but if I may ask a question about 2D again. So I forgot what your statement about the leg poles was. I mean, in the sense that if you have such a precise map between, worldsheet physics and target space physics, so clearly, the leg poles should just come out of your analysis or not?
Okay, this is of course not my analysis. I think the leg pole factors were settled reasonably well, as I understand, by this Harvard group, Baltazar, Rodriguez, and in, right? And basically, what they said is that if we normalize in the Liouville theory, right? I mean, there's a ambiguity normalizing the vertex operator, right? But if you normalize the vertex operators correctly, then all the leg pole factors get absorbed there.
But I thought that was a rather, tame that was a rather tame interpretation of leg poles, because there are these papers by Natsume and Kolchinsky and so on, where the leg poles were meant to be physically something interesting, in which you didn't have, of course, propagating gravitons or something, but there are this like the Coulomb gauge gravitons, which were exchanged between the pulses of the tachyon, and you could interpret the S matrix of the gravitons essentially, the S matrix of the tachyons with this graviton exchange, meaning not the transverse graviton exchange, but the sort of Coulomb gauge graviton exchange coming from the leg poles. You know what I mean? I mean, you look at the leading leg pole, and that was given an interpretation of being some potential induced by a fixed gravitational background. So
yeah, my feeling is that in the Liouville theory, right, what they did,
yeah,
is equivalent to somehow normalize the Liouville thing in such a way that that effect is automatically included in the definition of the vortex operator.
But if that is so, then all this physics would rich physics would go away, no, or no? I mean, how would they write the Natsume Polchinski paper?
Yeah, that I don't know. I mean, the point, maybe there is a way to interpret. Maybe one can say there is another way to normalize the vortex operator, which is more natural.
Mm-hmm.
And there the leg pole factors will come. But at least the way these people set it up, okay, they normalize the vortex operator in a certain way, and then made a precise correspondence between what you see from the matrix model and what we see from the Liouville theory. And once the normalization is fixed, then everything else you can compare.
But if you forget about the matrix model, suppose you are talking about the space-time physics the way you are doing it, from the string field theory point of view, then you have such a detailed understanding of space-time physics in terms of worldsheet physics. So wouldn't you have some natural interpretation of or not? I mean, maybe you need. I see. You're saying that it's only in comparison with matrix model results that this leg pole stuff comes.
Yeah.
I see.
You can probably introduce the leg poles by normalizing the Liouville result, the Liouville vortex operators in a different way.
Yeah.
Right.
Which is what they do presumably. But that may not be the most physical normalization of the Liouville vortex operators, right? Because there's
So I think then the question is from Liouville viewpoint.
Yeah.
Is there any preferred normalization, right? That is different from what the BRY paper used.
Yeah, good. Yes. So how,
Yeah, and that's not completely clear to me. I mean, that there is such a preferred normalization, but maybe there is. I mean,
right.
But any comparison between the two can only be made after you have fixed the normalization of the vortex operator, right? And that
that I agree. That I agree, of course. Yeah. Right. Yeah, thank you.
So I think they basically showed that there is an overall phase that you can absorb, overall momentum dependent phase.
Yeah.
And after that, it's completely automatic, the comparison between the two.
From the space-time point of view, is this the statement that you can take two actions and do momentum dependent field redefinitions?
That's that, yeah.
And since there's no clear notion of locality in this theory, in a normal quantum field theory, we wouldn't allow momentum dependent field redefinitions.
Yeah.
But here, it's not clear what the rules are.
Yeah.
I mean, one is the matrix theory, the other is this Liouville theory. Huh?
Oh, but I'm saying even just in space-time, you give me a space-time action, I can give you a new space-time action with a momentum-dependent field redefinition.
But as you said, normally we don't allow that because there's a notion of locality.
Yeah.
I'm just trying to understand your comment here. Because you have a matrix theory and Liouville theory, there is not a clear notion of
I was saying even that in string theory, the string coupling varies on string scale. So there's no translational invariance in any big dimension. So it's not clear what the principle is. Is that right, Ashok?
Yeah, I guess so. Yeah.
Nice.
Yeah. Okay, could I just, sorry, going back to 10 dimensions, I was wondering if you had 2D, in the next term in green and gut pearl would be 2 D-instantons, right?
Yes.
And if you had 2 D-instantons, there would be new complications. There would be these off-diagonal modes between the 2 D-instantons.
Yeah.
But you've dealt with them anyway, basically in your regulation scheme.
Yeah.
So it sounds like you're generalizing to 2 D-instantons will not be very difficult. Is that right?
Yeah. Yeah. But my feeling is that there will be some subtleties there. Okay, I have not thought very much about it, because naively what one would think is that if you have 2 D-instantons, the number of zero modes will double. Fermion zero modes.
Right.
And that will make this amplitude vanish. Right. So somehow it's the symmetry factor which has to save us, right? And how exactly does it? I don't know yet. But that's the subtlety one has to handle.
You might say the same about bosonic zero modes, right? I mean that the number doubles, but shouldn't one expect somehow that there's a potential generated between the two?
I agree. Yeah. Well, there's really no potential, right? But somehow there should be. Okay. My feeling is that it should be such that for this particular amplitude, right, we'll only get contribution from coincident instantons.
Yeah.
Because if they're far away, then the zero mode problem, I think you cannot avoid.
Okay. There were these old papers, Hollowwood, the old papers in the early days of ADS-CFT, trying to compare instanton calculations in Yang-Mills theory with the instanton calculations in ADS5 times S5. And if I sort of remember right, they just on the Yang-Mills side, they encountered sort of similar issues, and they had, in the end, they were asking, I can't really remember, but they had some sort of effective potential reducing the number of effective zero modes.
Yeah.
Would imagine something similar.
Something similar, yeah. That I mean, somehow it should be that only the coincident ones contribute. My feeling is that once one understands this better, it will be clear. It will be clearer than what we have to do in Yang-Mills, right? That getting this effective potential, etc. Yeah, it's a complicated process, right? My feeling is that if one can do it for D-instantons, it will probably be cleaner than what one would do in Yang-Mills instantons. And one analogy I can think of is in the index calculation. Normally, if you have, say, 2 BPA states, right? Say 2 identical BPA states.
Right.
You imagine that they will not contribute to the index because they have double the number of zero modes.
Right.
And it is true in general, right? But what one knows is that if we really consider the system of 2 D-instantons, then when 2 D-branes, when they're on top of each other, then because of the symmetrization, they can actually give a non-zero contribution to the index.
I see.
So something similar may happen here, right? I mean, it's maybe simply that somehow symmetrization will make the zero mode contribution non-vanishing. And even though naively it looks like that there will be double the number of zero modes.
Okay.
But that expected answer looks, reasonably complicated, so that one has to really think about it, how to get.
There are some Eisens, some funny numbers behind.
Yeah, basically you have a sum over, I think, integers which divide 2 in the case of D-instantons, right? It will be sum over 1 and 2, right?
Okay.
For N-instantons, it will be like sum over integers which divide N.
Okay, yes.
Right?
So it sounds interesting.
Yeah, I mean, the structure looks interesting, right? And it will be good to reproduce it from this.
Right. Other questions?
Sorry, but just to get your global perspective, since we have the opportunity, what other problems where D-instanton corrections might play a dominant role do you have in mind or you find interesting, Ashok?
Well, I think you are probably the best person to.
No, I'm totally out. I mean, this is way beyond my whatever pay grade ability level. But
D-instantons here means not just D-instanton, but any Euclidean D-brane. Right? The RAP D3 brane is also, the same analysis can go through.
Yeah, I see.
Right? Not just D-instantons.
Yeah. Yeah, no. So it would be tremendous. Yeah, in terms of beginning a systematic understanding of these compactifications and so on.
Yeah, and I should have said that also, I mean, this string filter is also useful for doing systematic G-string correction, right? Which I haven't described, which I described in the two-dimensional string theory context in this ICTS talk. And this, I know that this Harvard group is looking at it, right? Because this is in fact conceptually easier to fixing normalization is one point, right? But now suppose you have got instanton, the leading instanton contribution, this GS to be 7 up. And then there's 1 plus a constant times GS plus a constant times GS square, and all those can be systematically computed using the string field theory techniques.
Yeah, I see.
In the type 2B answer, what is the structure of that? Are there G-string corrections around?
There are no G-string corrections.
There are no G-string corrections.
No, there are. There
are known. And does it terminate or it?
No, it doesn't terminate. It just goes on.
Just goes on. Nice.
Yeah. So I know that this Harvard group, they are trying to calculate the first order G-string correction in this.
I see.
Which basically requires this annulus 1-point function and this 2-point function, the same kind of calculation that occurs in matrix model in the two-dimensional theory.
But to go and get the nth guy sounds impossible, right? Or unless something very fun.
Yeah, meaning impossible means unless you are doing want to do the calculation for the n that order, right?
Yes.
The worldsheet and sum them up.
Yes. So that sounds like enormously complicated unless you can use some localization.
Yeah, I agree. Yeah.
Okay.
I see. Ashok, this is tangential to your talk today, perhaps, but just, from the point of view of understanding flux compactifications and so on, just being able to compute corrections systematically once Ramond fluxes and so on are turned on, also is extremely important, just to even settle some of the current now controversies on whether these compactifications are controlled or not. Because, we felt, okay, this kind of flux has under control, but if someone challenges you, then what you really have to do is the next order calculation and show them. And I certainly didn't have the tools. Is that doable even without worrying about D-instantons? For example, just the corrections, in powers of G-string.
I think you need the D-instanton first, to stabilize the Kähler modulus. I thought you need Euclidean D-instanton.
Yes, you do.
Coefficient, I think, is important, right? Because that's what determines whether the corrections are under control or not.
Yes, very, very important. I totally agree with you. But I meant even a baby problem, which we do a supersymmetric compactification without stabilizing the Kähler moduli, but we check just in general, how do the higher powers of Ramond flux come with coefficients, because if there's some large 2 pi to the something coefficient, it can get your estimates wrong. That sort of thing, because if all coefficients are order 1, then you make some estimate, but you're never sure if you haven't been able to compute.
Yeah.
Is that doable, just systematically higher powers of flux correction?
Okay. Ramond, I think if you are interested in just expanding in parts of flux, it is doable in principle. Because then you are not worried about Ramond background, okay? But you just think of the Ramond flux as an external insertion, right? That you can do in the standard NSR formulation. You don't even need the picture changing. You don't even need the pure spinner, right? To any given order in the part of flux, if you want to expand.
I see. Right.
That I think in principle doable by standard string theory.
That is doable. Okay. Right. You're right. I see. I mean, it seems reasonable. Okay. Well, maybe I'll try to think of some clear enough calculation which might probe at least the higher order corrections, this idea that they are order 1 coefficients in some natural way of normalization, and then come back to you. I don't know, just even beginning to test that might be good, just to take the discussion forward in some constructive way, otherwise. And then, of course, with the D-instantons, as you say, there the normalization is very important, right? I see. Okay, thank you.
Any further questions? Okay, if not, let's thank Ashok for a wonderful talk as usual.
Thank you very
Thanks a
much.
lot, Ashok. Fantastic.
Thank you.
Thank you. Thank you very much, Ashok.
Thank you.
It's a treat.
Okay. Bye.